This problem is about finding the longest consecutive sequence in a list of integers. The challenging part is that it has to run in linear time, so that excludes the use of sorting, as sorting is inherently a O n log n um, complexity. So um, we would have to find an alternative, and I'll show you two kind of approaches that you can take to approach this problem. If you think about any list in a consecutive um, sublist, each subsequent number in a consecutive list is basically one bigger than the previous value. So we can definitively find out what the whether or not a value in a list can be a starting value or it can be an ending value. For example, you cannot have a starting value um, if there exists a value that is one less than it in the list, and you cannot have an ending value if there exists a value that is one bigger than it. So you might be wondering why knowing the starting values or the ending values help us find out what the longest sequence is. And that's because once you know definitively whether or not the value is at either end, then you can just work backwards or forwards depending on if you have the starting value, you will try to keep finding whether or not there exists a value that is one bigger than it continually until you reach a terminating point where there does not exist such a value. If you start with an ending value, you can do the same in reverse, where you're trying to find out numbers that are always one less until you hit a point where you can't find that. And the key word here is existence, as existence um, in any language is usually a constant time operation. For example, in Python, if you use sets, that is a um, implementation that uses a hash map, which is going to be in O1 time complexity. So that helps us avoid using nested for loops that would make it a um, that would fail to meet the requirements. So if you think about initially, if we know that, well, the edge case that there are no nums, then we want to return 0. If there are nums, then we can initialize what the global maximum length would be, and that would be 1 because there has to be at least one element. Um, I mentioned global here just because we will also be we'll be finding local maximums within our loop, because if we start from some value we know that is starting or ending, we don't necessarily know um, where that value lies in the sorted arrangement. So we will not be able to um, find out what the largest one is until the loop terminates. We will definitely need a set of nums. So we can define num set as a set of ints and just set that to set nums. Now we want to iterate over nums to find out um, either the starting values or the ending values. So we will kind of work with starting values, as that is a bit more easier to think about, but the same logic works in reverse. I'll show you that in a bit. So for in this, so we're trying to find um, a starting value so we can find a local max. And if you think about what it means to find a starting value, again, it is thinking about whether or not a value that is one less than it exists. So basically, if there exists a left neighbor in a sorted arrangement, then that cannot be a starting value. So if num minus 1 exists in our sorted set, um, that would not be a starting value. So we just need to invert the logic. So if that does not exist in our num set, then we know that it is a starting value. And we should also note that this is a constant time operation. So this is simply doing an existence check in the set of nums. We can also just specify that it is a left neighbor does not exist. So now we can, once we have this starting point, we can try to find out how far we can reach from this point, incrementing one at a time, checking each one whether that exists in our set or not. And that will help us find the local maximum. So we want to define what the local maximum width is, and that will also be initialized to 1. We will also need to keep track of our current value that we're at so that we can keep incrementing and checking whether that exists or not. So we can say current num, and we will be initializing that to the num that we're on. And then we would probably want to have a Boolean that keeps track of, well, it will help us break out of a loop. So we can know how to exit until if you don't find a number that is 1 bigger. So is greater true, and we assume it's true until we don't. So that's why we initialized it to 1, as we are assuming. Well, we always assume that the element we start out is already included in the maximum. So while not is greater, we want to basically check whether or not the num that is 1 bigger than it exists. So we can basically just increment our current num. And then we want to check if that num exists in these sort of sets. So if current num in set, and this basically means that left neighbor was, sorry, right neighbor was found. And that means that we can increment our local maximum as we found 1 more value. So, and this also means that we can, otherwise, if we don't actually find that right neighbor, then we have broken the sequence. So then we just basically say is greater equals false, and that will break out of that loop. Once we are outside of this loop, we want to check whether or not our local maximum that we found is greater than the global maximum. And if it is, then we can update it. So it's greater global. And this thing will continue for each num that basically is a starting num that we identified. So all of these checks are O1 again, which make it a linear overall linear time complexity. And at the very end, we just return the global maximum width. If you think about the logic here, if you instead of wanted to find the ending values, you would just do an num plus 1, not in num set, and then you would be decrementing these values and finding the checking if it is smaller, and that would give you the same result. Just one more thing is that it's actually not It's actually while is greater. Um, that'll actually help us break out of the loop. If you run that, then all the cases pass. So as a final step for the optimization, we can do several things. For example, we were iterating over nums, but we noticed that this might have duplicates. If nums has a lot of duplicates, this would lead to a lot of repeated calls. So that is a major optimization, as well as we don't need to have a boolean for the while loop. We can simply check whether the next number is already present using implicit incremented values. So um, that means we don't need this, and that would want to increment after we um, add to the maximum. And that would be the optimal solution. And if you just run that, um, it passes. And this same solution works in reverse if we want to start at the end. So using ending values, and we keep decrementing, that would give us the same complexity. And this is one of the fastest solutions, just depends on when you run it. You might get different results, but this is, at least in Python, is one of the, the optimal solutions. That's it for this problem. So thank you for watching. See you next time.